Welcome everyone. Today we are going to delve into one of the most impactful advancements in the field of natural language processing, that is BERT, B-E-R-T, BERT, which is developed by the researchers at Google. We have seen that how word embedding will convert a word into numerical vector of certain length. Here are certain words are there with us: ashes, Australia, cumins, cover, Dhoni, and Zimbabwe likewise. By capturing the relationship between the words in terms of like person, country, healthy fit, event, target, something else, the two words Australia and Zimbabwe, looking at the values of this 0.97 and 1, these two words are similar as they are countries. Similarly, the words cumins and Dhoni, as they are persons, looking at these values as they are persons and who are healthy and fit, these two are the words which are similar. This is how the word embedding can be done, which will convert the word into the numerical form. But here is an issue with word embedding. Looking at these two sentences, the meaning of the word fair in these two sentences are very different. In the first sentence, if we see the judge's decision was fair and just, this fair means unbiased, like an equal treatment. Whereas in the second sentence, if we see, we attended the book fair last weekend, this fair is the festival like fun activity. But what the word to vec will generate is, it will generate a fixed embedding vector for the word fair in both the context, which is not correct, where this fair has different meanings in both the sentences. What we need is, this is the issue with word embedding. So we need a model which can generate a contextualized meaning of the word, meaning that looking at the whole sentence and generating the corresponding number representation for the word is required. That is what called contextualized embedding. BERT allows you to do the exactly same thing. It will generate the contextualized embeddings of the words. If you see these two vectors, the values 1, 0, 0.9.1 and 2 and this one, for the same sentence, the judges where the word fair has a different meanings in different contexts, the BERT generates the contextualized embedding, which is too different for the words with a different context, for the same word with a different context. At the same time, it will capture the meaning of the word in a right way, so that here in the sentence, the teacher's assessment was completely impartial. Here the word impartial is very close to the word fair in the first sentence, so that the word has generated the embedding vector which is closer to this vector 1, 1.9, 0.8, 0.2, 0.2 likewise. You can observe clearly. So that we got the vector that is very close with the closed values. Similarly, if you see the sentence, like the literally festival featured numerous famous authors. Here is the festival is also a fun event, like an activity. Here is also like an activity. So the word festival is very close to the word fair in this sentence, so that it got generated the vectors which are closer to this word. So we can say that this BERT is very powerful tool which can look at the contextual meaning of the sentences to generate the vector representations. It can also generate an embedding vector for entire sentence. Let's say you are working on a movie review classification task, and here is the sentence. For the whole sentence, this BERT will generate a single vector. BERT will usually generate a vector of size 768 dimension that we are going to see in the coming slide. Now the question is, what is BERT? We have seen the encoder-decoder architecture of the transformers in the previous lecture session. This encoder takes the words simultaneously and it generates the embeddings for every word simultaneously. These embeddings are the vectors that encapsulate the meaning of the word and the context, which is a contextual representation of the words. This decoder will take these embeddings from the encoder and previously generated token from the decoder, starting with the start token, and generate the next word in the output sequence one at a time until the last token, end token, is appeared for the task like the machine translation, questioning, answering, and etc. This is what the basic concept of the encoder decoder architecture in the transformers that we have seen in the last lecture session. Overall, what the encoder learns is what is language, grammar, and context, whereas the decoder learns how one word relates to another word. Both of these can separately have an underlying understanding of the language. Because of this understanding, we can pick one part of this architecture and build systems that understand the language. Right? So thus, if we stack the encoders, we can get BERT model. Similarly, if we stack the decoders, we can get GPT. That is not shown here. We're just focusing on BERT. Thus, this BERT is a stack of encoder transformer. So, BERT is a bidirectional encoder representations from transformers, where the encoder representation from transformers is what just we have seen. And as the BERT is pre-trained on the massive amounts of data, these encoder representations generated by the BERT are very high quality, and they already have a good understanding of the relationship between the word and the context of the sentence. This is what make this BERT as very easy to fine-tune for the specific task. Now, this bidirectional part refers to the fact that attention mechanism in the encoder can look at both the past and the future of any selected word, allowing it to better understand the context of the word. Better understand the context of the word. So, BERT is basically a trained transformer encoder stack. There are two sizes of the BERT. One is the BERT base model, and second is the BERT large, which is a ridiculously huge model which achieved the state-of-art results. Both of these models have sizes and have the large number of encoder layers. There are 12 encoder layers we can see in the BERT base version, and 24 encoder layers we can see in the BERT large version. These also have the larger feedback neural networks. We can see 768 feet in the BERT base model and 1024 hidden units in the large model respectively. And the attention heads could be here in this base model 12 attention heads, and in this large model we will have 16 attention heads. Then the default configuration in the reference implementation of transformers in the initial paper, where there are 6 layers, encoder layers with the 512 hidden units and 8 attention heads. These were the enhancements made. Now how this BERT was trained. BERT was trained on the Google with the 2,500 million words from Wikipedia and 800 million words from different books. Google trained this model using two approaches. How it was trained means two approaches it uses. One is the masked language model. Look at here. To understand this, just see here is an article on Elon Musk. What the researchers did while training this model on the masked language modeling approach, they had masked the 15% of the words in this sentence. Nothing but they left it as the blanks. For example, the words entrepreneur, SpaceX, Tesla, etc., etc. And they generated these training samples and trained the BERT model with the goal of predicting the right word into the blank. Unlike the traditional language models that predict the next word in the sequence, BERT randomly masks some of the words in the input and tries to predict them. This helps the model to understand the context better because it looks at the entire sentence to predict the word. Using the AI models when they train their BERT model, as a side effect, they got the word embeddings. So the end purpose is to get the word embeddings. So the masked language model is a meaningful task used to train the BERT model, and as a side effect, you get the meaningful word and sentence embeddings. The other way how this BERT model was trained is on the next sentence prediction approach. For example, if I say there is a sentence, I'm hungry, predict the next statement like, I would like to eat pizza, or the table has 4 legs. Here, if you look at, there is a more probability for the sentence, I would like to eat pizza, as the next sentence to the given sentence, I'm hungry, than the second sentence, table has 4 legs. The meaning, the model will be given two sentences that are supposed to either come one after another or not. And the model goal is to tell whether they belong together or they do not. This is what next sentence prediction approach. Using this masked language and next sentence prediction approaches, the researchers were able to get a really well-performing language model BERT. And today Google search is powered by this BERT, and search has become more directed after they onboarded this BERT onto the search engines. Thus is the power of BERT. Not only for masked language modeling and next sentence predictions, BERT might be used for many other tasks. For that, what you need is fine-tuning. So using this pre-trained BERT model as a foundation for solving the specific tasks such as the classification, sentiment analysis, and named entity recognition or question answering is nothing but the concept of transfer learning with BERT. That way, the meaning of the transfer learning was discussed in the previous lecture session. Just revise once again. So BERT uses a two-step process. One is the pre-training and the second is fine-tuning. BERT will be pre-trained on a large corpus of text from the internet and learns to predict the missing words in the sentence by the masked language modeling, and to determine if one sentence follows another using the next sentence prediction approach. This is the pre-training phase. Then the next phase is the fine-tuning. After pre-training, BERT can be fine-tuned for the smaller task, and that is the task-specific datasets, such as the sentiment analysis, question answering, email, spam, text classification like spam detection, likewise, named entity recognition, whatever is it. While fine-tuning the BERT, basically you need two things. One is new output layer that will be plugged at the end of the BERT, that is specific to your task, that what you are trying to perform. And the second thing is the data set that is specific to the task that you are trying to achieve. For example, if you wanted to do sentiment analysis, you basically need to plug in an output layer of neurons after BERT layer that can classify the input that it gets from the BERT, which will be the output of BERT into different sentiment labels. Now let's try to explore this BERT model. Google for TensorFlow Hub to find the BERT models. Then look at the models. If you click on the models, you will get moved into the Kaggle. This you need to notice that TensorFlow Hub is moved to the Kaggle model, so you can get these models in the Kaggle. Find the model here. From the models, you can get BERT model. All models. From these models, you can see the BERT models. You can browse it or just type it, BERT base model. TensorFlow BERT model. This is the base models. Different versions of the models you can see from here. TensorFlow versions. You can see. choose the model whatever you want. With each of the model, there could be an associated preprocessor with each of the model. Here is one model we have chosen. With each of the model, there is a corresponding preprocessor would be there, which will be used for preprocessing the text using that which is suitable for that particular model of specified dimensions of encoders and a number of layers with the attention heads. Both the things to be downloaded along with the model, and these things to be downloaded. So both this birth model and pre-processing model to be downloaded, that you can do using the hub.keras layer. For doing all these things, that I'm taking into this Google Colab notebook. So I took this uncased BERT uncased preprocessor along with the model, 12 encoder layers, and with hidden nodes 768 and 12 attention heads. These two models. This is the BERT model we have chosen. That you can with this by taking that path of the model which is available in the TensorFlow Hub, we created the layer BERT model by the hub.keras layers using. Similarly, for the preprocessor as well, we did the same thing using hub.keras layers. We created the preprocessor. So both the preprocessor and the model were downloaded. Pre-trained models were downloaded into the variables preprocess and the BERT model. For doing this, first of all, we need to import the required libraries. So we imported the TensorFlow Hub and TensorFlow Text. In order to work with the TensorFlow Text, before that, you need to install the TensorFlow Text version of some specified version or upgraded version, whatever it is. So that's the first thing that to be done. Once all these things are done, the next thing is we need the dataset. Here is a sample dataset that I had created with the 2 sentences. This is such as an amazing movie, and I like transfer line some text, which is a sample dataset like a classification task. And the first step is we need to process this text using the preprocessor, BERT processor. So this text was passed to the BERT preprocessor and displays. The result of this operation is a dictionary. Let's have a look at the keys of this dictionary. These are the keywords that you can find with this dictionary: input mask, input IDs, and input word IDs. There could be 3. We will see the individual elements of this one. Let's take input mask. Let's see the input mask first. For these 2 sentences, this is the output that we got it with the input mask, preprocessor tests of input mask. If you look at the shape, it is 2 by 128, meaning that there are 2 sentences that we have taken, and each is of maximum length 128 including padding. So this is the mask of the first sentence, and this is the mask of the second sentence. We are trying to capture the input marks of the preprocessor text. This is the masking done for the first sentence. This is for second sentence. Look at the first sentence masking. There are how many masked tokens? 3 plus 3 plus 3. 9 masked tokens are there. But coming to the sentence, if you look at the initial sentence, first sentence, there are 7 words including the exclamatory marks. 2, 2, 4, 6, 1, 7, including exclamation marks. There are only 7 tokens in the first sentence. But while coming to the input masking, you got 9 tokens in the masking of the first sentence. 9 ones you got. 9 tokens where masked tokens were there. What is the difference? What is these 2 extra? Thing is, so when BERT is processing the sentences, it always put a special token CLS. We can see somewhere in this one, but original model, if you look at the original model of the BERT, that we can get it there. About the description of the BERT. at here somewhere. Okay. For the sentence, when BERT processing the sentences, it always assigns put a special token CLS along with the sentence. It will put a special token CLS at the beginning and separate another token SCP as a separator of the sentences. These two will be the additional tokens which will be assigned to each of the sentences while the transformers of the BERT is masking the input text. So with these two additional tokens, masked tokens, now it has become 9. Masked tokens are 9. This is 7 plus 2, 9. So look at the second sentence. I like transfer learning. Actually, there are 4 words in this. 4 tokens are there. Word tokens are there. 4 plus 2, 6 word tokens you will get masked. 2, 4 to 6. It's very clear. This is what the meaning of masking the input sentences. Hope you understand well. We'll look into the another individual dictionary element, that is the input word IDs. If you look at the input word IDs of the preprocessor, the processor text input word IDs, here we can see that these are the individual IDs of the words in the vocabulary we will get with this. These are the individual word IDs. 9 for the first sentence, 6 for the second sentence. Look at carefully, you can grab it. 101 is the first token in both the sentences and 102 is the last mask token in both the sentences. The meaning that this 101 is the ID for the token CLS, first token CLS, and 102 is the ID for the token separator SCP. These are the fixed values. And rest of all the values, what you can see here, 0 are the padded values of the sentence of maximum length 128. Each sentence is, both the sentences, whatever it says, are maximum length 128, they have been padded. We'll see another one, input type IDs. In this case, we got all zeros. This is not that important right now, so I'm just leaving this. Once preprocessing is done, then we have to apply BERT model to this preprocessor text. We already downloaded this BERT model. We created a layer with the BERT model. This BERT model is being passed this text processor. Processor text is being passed to this BERT model and got the results. This result is output of the BERT is also a dictionary. So look at the key elements, individual elements of this dictionary. We can see this. Encoder on outputs, pooled outputs and sequence outputs. Let's see one after other in detail. This pooled output is the most important attribute that we need to, dictionary key that we need to focus on. If you look at the results pooled output, you can see the shape of this tensor is 2 by 768. Meaning there are 2 sentences, each of 768 embedding dimension. If you see the sequence output, second one, sequence output of the sentence, this is the individual word embedding vectors. Looking at the shape, you can see that 2, 128 and something, meaning there are 2 sentences. Full sequence length is 128 including the padding, and each of the token is of 768 embedding dimension. For even padding, you can see this, you got the values even for padding because it is a contextualized embedding. This is the first word token of the first sentence, second word token of the second sentence likewise. Now let's look at the encoder outputs. If you see the length of the encoder output, it is a 12 because we are using a small bit based model with the 12 encoders and each has a 768 embedding dimension vector. So this encoder output is the same as nothing but the sequence output. So we can confirm this here. Look at this. Yeah, same as this one. And if you look at the last layer of this encoder output is nothing but the sequence output. Both are same. This we can confirm here from here. So the last layer of encoder output is nothing but the sequence output. So when you are building any model, BET model for fine tuning your own specific task, we need to get this pulled output, which is nothing but the entire sequence, full sequence embedding representation. Yeah, given a raw data, this is the way here I try to visualize what is this BET model implementation. Given the input sequence, this BET tokenizer will divide it into the token IDs, input masks, and the input type IDs. Those are the three dictionary words that we have seen here. With the pre-processing stage, nothing but the tokenization of the BET. Once these three will be given as together, will be given to the BET layer, BET model layer, which will produce the pulled output that we have seen here. Pulled output that we saw the output of this BET model. This pulled output then will be given to the Keras model of your own choice of layers with the feed forward layer, dropout layer, and whatever is required at the end, like for the classification layer, feed forward layer for the classification task. So thus the model will be built. What we have seen just now is building and exploring this BET model using TensorFlow Hub. Now I can show you how to use this BET model using Hugging Face transformers as well for your convenience. For this, what we need to do is, first of all, we need to install the transformers. Once the PIP install transformers from Hugging Face, once it is installed, then from transformers we have to download. In order to download the BET model and the tokenizer, first we need to import this BET tokenizer and the TensorFlow BET model. Two things, these to be imported. Once imported, we need to load the models using the from underscore pre-trained method of the tokenizer and from underscore pre-trained method of the corresponding model. So BET tokenizer with the imported tokenizer model using the from pre-trained method, we imported the BET base uncased model and BET base uncased tokenizer. Both were loaded into tokenizer and the model. Done. Once this is done, rest of the part is similar. So I just took one example sentence. Hello, how are you? Then tokenize this text. This text is to be tokenized using the tokenizer what we had instantiated. So pass this text to the tokenizer and the result should be in terms of a TensorFlow vector. So written tensor type should be mentioned as the TF. TF is for TensorFlow. Then you will get the tokenized inputs of the given text. Then these inputs will be given to the loaded model of the BET model, which already been loaded into the variable BET, and these are the outputs to get generated. With these outputs, what you will get with the TensorFlow, with the Hugging Face transformers, you will get the states, these attributes. I mean to say, yeah, you can see the states that you will get is the last hidden state and polar output. Two things you will get. You're supposed to use this, whatever is the required, based on the required. So see the last hidden state, shape of the last hidden state. If you see 18768, embedding dimension is 768 of the sequence length. Look at the sequence. I didn't mention the padding. Here the padding was not mentioned. So while tokenization, padding was didn't mention. So it took the exact length of the sentence. How many words are there? Hello, how are you? 1, 2, 3, 4, 5, 6, including the comma and the question marks. 6 tokens are there in the input text. With added 2 special tokens of CLS and separator, it become 8. So as I didn't mention the padding here while tokenization, it just took the entire sentence. So the output of this model is the last hidden state information is one sentence of length 8 tokens, each of dimension 768 size. You can try with the two sentences. If you try with the two sentences, to make all the sentences of equal length, obviously we need to specify the padding to be done while tokenization. This is what I did it here with the parameter padding equal to true and the truncation is true, so that the both sentences will be of the equal size, and the output you can see here 9. So to the maximum length, the truncation padding is true and the truncation is true, I didn't make, so that the maximum length of the sentence is this one 9. So it's made it as 9. Actual sentence is of length 7, with added 2 tokens it became 9, it will become 9. So the same 9 is applied even for the sentence length is 4. So both the sentences have the length 9 and each of the dimension 768. We'll see the output, pulled output layer also, same as like this. So this is how BERT will function with the two steps of loading the model along with the preprocessor and using the model, process the text, while fine tuning this task for your own specific task also. So once the data set is chosen, then we have to pre-process the data, and we for the specific dot what we are going to work on, then pass this input to the BERT model by specifying the required output layer, which is according to your specific task of classification, clustering, and whatever it may be. Name identity recognition likewise. Thank you.